welcome to the deep dive. Today we're really getting into the weeds, taking apart the mechanics of modern AI agency. We're specifically tackling that, that Achilles heel, long horizon reasoning and our source material. It's this really dense, cutting-edge, archive preprint. WebResearcher, unleashing unbounded reasoning capability in long horizon agents. Just out from Tongyi Lab Alibaba Group.
Yeah, and this is definitely for listeners who get that we need more than just better prompts now. We're talking real architectural innovation. It's not about tweaking parameters anymore. No, we're looking at how to solve these fundamental structural limits, the things stopping LLMs from doing that sustained, rigorous research, the kind that holds up over dozens, even hundreds of steps without falling apart due to noise.
Exactly. And we've got, three big pieces to unpack from this paper's approach. First, there's the core mechanism. They call it research. It's this iterative deep research idea that totally changes how agents manage state and memory.
A whole new paradigm.
Then second, you need the fuel for this engine, right? That's Web Frontier. A really interesting scalable data synthesis engine built to train models specifically for these complex, multi-step reasoning tasks.
Which is a huge bottleneck right now, getting that kind of data.
Absolutely. And third, the performance booster, the research synthesis framework. That's for optimizing things at test time for scaling up.
Right. And the problem they're fundamentally aiming at here is, it's central to where AI is heading. It's about those scaling constraints, the way linear context accumulation just breaks down. If an agent can't reliably do long-term research, it's just not going to function as a true autonomous researcher. Simple as that.
Okay, so let's unpack that core challenge first, what the authors call the mono-contextual constraints. This is the trap most current agents seem to be stuck in.
Right. So if you look under the hood of, almost any standard LLM agent doing multi-step research today, it works, linearly. It faces a task, maybe a long horizon one needing dozens of searches or code runs or website visits, and it just records everything, every single piece of retrieved info, every intermediate thought, every little reflection. It all gets piled into one single context window that just keeps expanding.
I always picture it like a detective's whiteboard, Starts off clean, great for the first few clues.
Good analogy.
But after days of investigation, every single note, every phone number, every maybe irrelevant detail is still up there. The detective just can't see the connections anymore. The board's just full.
That's exactly it. And the paper points out two very specific consequences. First, what they call cognitive workspace suffocation.
Okay.
That fixed token limit, your budget, essentially gets swamped by just remembering the past. Old data. The model spends all its attention just keeping track of previous steps instead of using those precious tokens for, actual deep reasoning about what to do next.
So it's forced to jump to conclusions too early because it literally runs out of space to think.
Precisely. It can't do the synthesis needed. And the second problem is, arguably even worse for these complex, messy tasks, irreversible noise contamination. Okay. Yeah. So if it picks up something wrong early on.
Exactly. Say, turn 5, it pulls a slightly off-topic search result, or maybe an initial thought it had was just a bit flawed. In the linear model, that piece of noise, it just stays there forever.
There's no way to get rid of it or mark it as irrelevant later.
Nope. No built-in way to filter or revise or even just forget. So that noise hangs around, it dilutes the actual useful signal, it can propagate biases.
In over 50 steps, that early error can make the final result completely useless.
Totally. And the agent has no structured way to course correct or dismiss that old contaminated data.
Okay, so that sets up the need for their big architectural shift. In research, replacing that linear pileup with something iterative, and they frame it as a Markov Decision Process, an MDP. That feels like a significant conceptual jump. Why an MDP for research? Well, think about what an MDP is fundamentally about. It's about states, transitions between states, and choosing optimal actions in each state. By framing research this way, they're imposing a kind of structural discipline. They're saying an investigation isn't one long, unbroken thought stream.
Right.
It's a series of discrete steps, moving from one synthesized state of knowledge to the next. The crucial bit is the Markov property assumption. The decision for the next step only needs to know the current synthesized findings, not the entire messy history of how we got here.
Okay. So that allows for this iterative synthesis and reconstruction you mentioned. You periodically consolidate everything into like a summary report.
Exactly, a synthesized report.
And then you rebuild the workspace, focusing only on that latest high-density state.
Precisely. And look at how they define the state. This is where the architectural constraint really bites. It's deliberately compact. At any given round, the state explicitly throws away the raw history of all the past tool responses and internal thoughts. It only contains three things. 1, the original research question. 2, that stays constant. 2, the evolving report. 3, I1, which is the synthesized knowledge from the previous round. And 3, the immediate context from the very last action and its result. Text action I1 and text tool response I1.
I see. So that structure is what actually enforces the Markov property in practice. The decision at step U literally only sees the distilled knowledge from I11 plus the newest piece of information.
Yes. It's the architectural guardrail against that cognitive workspace suffocation. You're only carrying the essence forward, not the clutter.
And to manage this process, this transition between states, they structure the agent's thinking into 3 categories within each loop.
Yep.
Think, report, and action. These sound like roles in human research almost.
They map quite well, actually. Let's take think. This is like the agent's internal scratch pad.
Okay.
It's where it does its internal reasoning, reflects on the last step, was that search useful,
Right.
spots maybe conflicts in information, formulates a plan for the next action, all the internal cognitive work.
But the key difference from, say, standard chain of thought.
Right, the critical part, and the paper stresses this think content is not carried forward to the next state 7. It's ephemeral, used for planning the current step, then discarded.
To prevent exactly that context clutter we talked about.
Exactly. Which brings us to the report. This is the heart of it, the central memory component. And it's where the real innovation lies, I think. Because here, the agent doesn't just, append new findings to a list. It has to actively integrate the new stuff with the existing report. Really?
So it's doing synthesis on the fly.
Yes. It requires complex reasoning. Resolving conflicts between old and new info, updating conclusions if new evidence demands it, summarizing everything into a coherent, dense summary. Think back to your detective. They don't just staple new notes onto old ones, they write an updated case report, integrating everything known so far.
And that process is the main defense against the noise contamination problem.
Absolutely. It forces filtering and abstraction.
So the report is the anchor, the thing that provides continuity across potentially unlimited steps, precisely because it forces the model to constantly condense and refine its knowledge.
You've got it. And finally, the action component. This is pretty straightforward. It's the agent's interaction with the outside world. It can be a text tool call, hitting a web search, using the academic text scholar tool, maybe running some Python code, or it's the text final answer, which obviously stops the research process for that question.
What really strikes me here is how this design flips the agent's priorities. It's not about gathering the most data anymore. It's about the quality of the synthesis.
Exactly.
And because that synthesized state stays compact, it enables, at least in theory, research that can go on for an incredibly long time without degrading. Unbounded depth. Okay, so you've got this elegant architecture, iterative. But an architecture is only as good as the data you train it on, right?
Absolutely.
And the authors point out quite rightly that standard Q&A data sets just don't cut it. They don't train agents to do the hard stuff. Complex tool use, juggling information from multiple sources, figuring out contradictions.
Right. That's the capability gap. And it's a major bottleneck, not just model size anymore. We lack training data that truly demands active knowledge construction, not just passive recall.
So that's where Web Frontier comes in. It's their answer to generating this high-complexity data at scale.
Yeah, it's a pretty sophisticated setup, a 3-stage multi-agent system that actually bootstraps itself to create harder and harder examples.
All right, let's walk through it. Stage 1 is seed data generation. How did that start?
It starts with gathering a diverse, high-quality base corpus things like web pages, academic papers, ebooks. They then use what they call a summary agent to process this raw stuff.
Okay, so cleaning it up.
Yeah, cleaning artifacts, but also distilling it, taking long documents and breaking them into smaller, information-dense chunks.
Got it. Dense chunks.
Then these chunks are grouped together based on themes. They call these composite units. This is the first little step towards complexity.
Because the questions will need info from multiple chunks within that unit.
Exactly. Ensuring that even the initial questions inherently require pulling from different related sources, maybe from different original documents. It moves beyond just simple lookup. Then an item writer agent takes these composite units and generates the first batch of seed QA pairs.
Okay, so that's the seed. Now, stage 2 sounds like where the magic happens. Iterative complexity escalation.
This is the core of Web Frontier, I think. It's where they turn it into an engine for creating really challenging frontier-level training data. The item writer agent gets upgraded here. It gets access to all the tools the final agent will have. General web search, the text scholar tool for academic papers, a web page browser tool, and even a Python code interpreter.
Ah, okay. So it can now act like the agent it's trying to train.
Precisely. And it uses these tools in 4 specific predefined ways to systematically make the existing QA pairs harder, more complex. It's like structured self-improvement for the data set.
Let's break down those 4 operations. First one is knowledge expansion. What does that involve?
Knowledge expansion is about broadening the context. So take an existing QA pair. The agent uses its search tools to find related but maybe secondary or tangential information.
Like if the question's about algorithm X.
Yeah, maybe the expansion step looks for the lead researcher's other work or asks about real-world applications of algorithm X that weren't in the original source docs. Then, the new question forces the agent being trained to synthesize the original facts, plus these new expanded details requiring tool use to bridge the gap.
Okay, makes sense. Broadening the scope.
Yeah.
Next is conceptual abstraction. Sounds like moving up a level.
Exactly that. Taking concrete facts and pushing the agent to identify higher-level principles or maybe spot subtle links across different domains.
Can you give an example?
Sure. Say the seed question was about the specific energy yield of one chemical reaction. The abstraction operation might reformulate it to ask about the underlying thermodynamic principle governing all reactions of that type.
Ah, okay. That might require searching physics papers, not just chemistry.
Right. It forces synthesis across fields and trains that abstract reasoning capability, which is vital for the think part of ITER research.
Okay. Third operation, factual grounding. This sounds like it's about accuracy.
It is, very much so. This is about forcing multi-source cross-validation. The system might deliberately introduce slightly conflicting info or very nuanced details into the prompt. This forces the agent solving the problem to use its tools, maybe hit multiple independent sources, to confirm a fact or resolve a discrepancy.
So it's training the agent to be skeptical and thorough, to handle real-world messy information.
Exactly. It directly trains those filtering and conflict resolution skills needed for the report synthesis in ITER research.
And the fourth one, computational formulation. This must be where the Python interpreter comes in.
Yep. This operation takes maybe a conceptual question and reformulates it so that answering requires actual calculation or simulation. You might take a question about, say, market trends and turn it into a problem requiring the agent to write and run a small Python script to calculate a specific growth rate or simulate a simple scenario.
Which has the nice side effect of making the answer objectively verifiable.
Huge benefit. And it trains the agent to translate natural language requirements into working code. This whole cycle, expansion, abstraction, grounding, computation, taking existing pairs and making them harder using tools, it just keeps bootstrapping. Complex pairs seed even more complex ones.
A virtuous cycle, as they say. Okay, but how do you ensure quality? That leads to stage 3, rigorous quality control. You need to make sure this generated data is actually in that sweet spot, hard but solvable.
Right. They use a smart 2-step filtering process. First, the baseline filter. They take a question solver agent, but, and this is key, they run it in a basic mode without access to any of the external tools.
Okay.
This baseline agent tries to answer the generated questions if it gets it right.
Then the question was too easy. Didn't require tool use or complex synthesis.
Exactly. So that QA pair gets tossed out. It's filtered out as too simple for what they need. This stops the dataset getting bloated with easy recall-based stuff.
Smart. So what happens to the pairs the baseline agent couldn't solve?
Those harder pairs move to the next step. Now, the question solver agent gets its tools back. It runs in the advanced tool-augmented mode, just like the final WebResearcher agent. If this agent, with all its tools, can successfully solve the problem, then bingo. That's a high-value, complex reasoning example. It's kept for the training set.
And if even the advanced agent fails?
Those pairs are either discarded or flagged for a human expert to look at. This minimizes the chance of including flawed, unsolvable, or just plain bad questions in the final dataset.
And they use a couple more agents for quality control too, right? A judge agent and a similarity score.
Yeah. The judge agent is basically for automated correctness checking against the ground truth answer during that validation phase. Standard practice, but important. The similarity score, though, is really crucial for maintaining dataset health at scale.
Why is that?
Well, when you're auto-generating millions of QA pairs, It's really easy for the system to fall into ruts, generating lots of questions that are just slight variations of each other semantically redundant.
Dataset mode collapse.
Exactly. The similarity scorer's job is to detect and filter out these lookalike pairs. This ensures the final Web Frontier dataset stays diverse, covers a wide range of reasoning patterns, and doesn't just overfit to a few common structures. That diversity is key for generalization.
Okay, so putting it together. Editor Research gives you the architecture to handle long chains without memory overload, and Web Frontier generates the specific, complex, tool-requiring data needed to actually train that architecture effectively. A powerful combination.
Right. So now let's get into how they actually train the ITER research model using all this carefully crafted Web Frontier data. The first step they highlight is rejection sampling fine-tuning, or RFT. This sounds like it's key for getting the agent to even learn this new structured process.
Yeah, RFT seems crucial. The idea is, for a given question from Web Frontier, they prompt the LLM to generate multiple possible research paths or trajectories following that whole structured think, report, action sequence.
So the agent is basically trying out different ways to solve the problem using the new format.
Exactly. But here's the critical part. The strict rejection sampling. They only keep a trajectory for fine-tuning if the final answer it produces exactly matches the known correct answer from the Web Frontier dataset.
Wow, okay. That's a really high bar. Not just did it look reasonable, but did it get the right answer?
Precisely. And the implication is significant. It means the model isn't just learning to generate plausible-sounding text in the right format. It's learning to follow a complete reasoning process, thinking, synthesizing, using tools, filtering noise that actually leads to the correct conclusion. They're fine-tuning the entire path, not just the end result.
That makes sense. You want the whole chain of reasoning to be high fidelity.
And this feeds directly into their formal training objective. They aim to maximize the conditional log likelihood across all those accepted trajectories. The paper gives equation 1 for this. Sum j high, sum j1, jsi, sij.
Okay, and the structure of that equation itself reinforces the architecture, right?
Exactly. Look at the conditioning term, beta side 5. The structured response twaddle, which includes think, report, action at round JSI, is conditioned only on the state values from the immediately preceding round, JD$1 enter.
Which contains that compact synthesized report.
Right, so the training objective itself is explicitly forcing the model to learn the Markov property. It's trained the model to rely on that high-density report as its working memory, rather than trying to implicitly look back over hundreds or thousands of raw tokens like a standard LLM might try to do.
Okay, so RFT bootstraps the basic ability. Then they move into reinforcement learning, RL. And here, this iterative structure gives them a big practical advantage, data amplification. How does breaking a task into rounds boost the data?
Well, think about the old mono-context way. If an agent takes, say, 50 steps to solve a problem, you get one training sample, that whole 50-step trajectory.
Okay.
With Editor Research, because each round J$ is treated as a self-contained state transition based on the compact state ZJ1, that single 50-step trajectory actually breaks down into 50 distinct training samples.
Yeah.
Each round becomes a learning opportunity.
I see. Sample J$ learns to generate response, given state, live a J1.
Exactly. So if they generate different trajectories, rollouts for each of $1 questions, the total number of training samples, D total, isn't just $$ times DG. It's the sum of the lengths of all rounds across all trajectories. Sum of DG, this is way, way larger than $1. A massive increase in usable, high-quality training data from the same number of simulations.
That's a significant efficiency gain. More learning bang for your compute buck.
Definitely. But it does create a bit of a technical headache for distributed training.
Because the trajectory lengths, 2 DGellers are all different.
Exactly. Some problems might take 5 rounds, others might take 60 or more. So the total number of sample total isn't fixed. But large-scale distributed training, especially using data parallelism with a fixed number of GPUs, DP size phonius, really wants consistent equal batch sizes on every device.
Right. Variable batch sizes mess up synchronization and load balancing. So how do they handle that?
They used a pretty standard technique. Minimal loss downsampling. Basically, they calculate the total number of round samples they have, saddleable, and then they slightly reduce it to the largest possible number that is perfectly divisible by the data parallel size, DP size.
So Sal floor C total DP size.
All floor times DP size total.
Yeah, precisely. This ensures every GPU gets the exact same number of samples per batch, keeping the training stable and efficient. And they note the data loss is minimal, typically less than 1%, so you're not throwing away much valuable data.
Okay. Practical solution. Now, for the RL optimization itself, they used Group Sequence Policy Optimization, GSPO. Why that specific algorithm?
GSPO is well suited for optimizing policies and sequential tasks like this. The key advantage they leverage relates to how RL calculates the advantage estimate, basically, how much better or worse a particular action was compared to the average.
Advantage estimation is critical but can be noisy. Right. And normalization helps stabilize it. With GSPO, they do the normalization smartly. All the rounds originating from all the Devil 2 directories generated for a single initial question to group together for calculating and normalizing the advantage.
Okay, so you're comparing actions taken across different attempts to solve the same underlying problem, even if those attempts had very different lengths or took different paths.
Exactly. Even though the trajectory lengths $2 might vary wildly, the ultimate goal, solving question $2, is the same for all trajectories in that group. This grouping strategy allows them to benefit from the massive data amplification, treating each round as a sample, while still performing the advantage normalization in a way that's structurally meaningful for the overall task. It gets them stable RL updates despite the variable sequence lengths.
Clever. It marries the per-round learning with the per-task objective. Okay, so IDA makes a single agent much more capable, much more robust for long tasks. But, to really push performance on leaderboards and challenging benchmarks, single agent performance often isn't enough. Usually needs some kind of ensemble or test time scaling.
Right, like running the model multiple times and combining the results somehow.
Exactly. But here's the snag. If you just ran, say, 8 parallel WebResearcher agents, each doing its full multi-round thing, and then tried to feed all the raw context from all 8 trajectories into a final model,
you'd hit the context limit immediately, or the processing time would explode.
Precisely. That quadratic scaling of attention would kill you. It's just computationally infeasible for these potentially very long multi-round histories.
So that compact high-density report generated by Edda Research has to be the key again, and that's what the research synthesis framework is built on. It splits test time scaling into 2 phases.
Right. Phase 1 is just parallel research. You spin up $1 independent research agents. Each one uses the full iterative process think, report, action loops to tackle the target problem on its own.
And because there's randomness, tool interaction variance, etc., each of these NOG agents will probably explore a slightly different path.
Yeah, they'll likely use tools differently, synthesize slightly different intermediate findings, maybe even reach different conclusions. The output of this phase, as shown in equation 6, isn't the raw trajectories. It's just the set nuller containing the final report and the final answer from each of the NAGIANTs, each of the N $1.
Okay, so instead of null or potentially massive multi-hundred turn histories, you just have no pairs of final summarized knowledge, final answer. Much more compact.
Massively more compact, and that's the crucial efficiency insight. This compact set nullers is then fed into phase 2, integrative synthesis. Here they use a single, powerful synthesis agent. The paper mentions they used Quen 3 235BA22B for this in their experiments. Its job is to take all final reports and answers from set nullabor
and make sense of them.
Exactly. Cross-validate them, maybe reconcile conflicts if the agents disagreed, identify the most robust conclusion, and generate one final synthesized answer. Equation 7 shows this. Text, final answer.
The cleverness here is really in the token budget, because each final report already distills the essence of an entire, potentially very long reasoning path. The single synthesis agent can effectively evaluate and compare the different solution strategies, do the different knowledge summaries, all within a manageable context window. It's like reviewing another executive summaries instead of another binders full of raw notes.
You got it. It lets them get the main benefits of ensemble methods, leveraging diversity, redundancy checking for robustness, without paying the huge computational price you'd normally associate with aggregating context from multiple long chains of thought. It makes test time scaling practical for these really long horizon agent tasks.
All right, so the architecture sounds good, the data generation is clever, the training is sophisticated, and the scaling approach makes sense. But does it actually work? Let's look at the experimental validation.
Yeah, the proof is in the pudding. They tested WebResearcher extensively across 6 pretty challenging benchmarks. These cover a good range. Humanities Last Exam, or HLE, for deep academic knowledge. BrowseComp in both English and Chinese for complex web navigation. GAIA for tricky goal-oriented tasks. XBench deep search. And Frames for RAG-style synthesis. A diverse set.
And the main metric was pass at 1, So getting the answer right on the first try.
Correct. Pass at one, verified using an LLM as a judge approach, which is becoming standard practice.
Okay, let's start with the general reasoning benchmarks. HLE, humanities last exam, sounds tough. Lots of niche academic stuff.
Very much so. Requires deep synthesis. And here, WebResearcher Heavy, their scaled-up version, achieved 36.7% accuracy.
How does that stack up?
Well, it's a pretty significant jump over the other powerful proprietary systems they compared against. DeepSeek v3.1 got 29.8%, and OpenAI Deep Research managed 26.6%.
Wow, okay. So that 6.9 percentage point lead over the next best is substantial. That really does suggest the research approach helps maintain reasoning quality for complex synthesis.
It does. Now, moving to BrowseComm, this is all about dynamic web navigation, scrolling, clicking, extracting info over potentially very long sequences.
All about interaction than pure knowledge.
Exactly. And here, WebResearcher Heavy hit 51.7%. This was basically neck and neck with OpenAI Deep Research, which got 51.5%.
Okay, so competitive at the top end.
Yes, but crucially, it massively outperformed the next best open source system they tested, DeepSeek v3.1, which only got 30.0%.
Oh, a 21.7 point gap. That's huge.
It's enormous. It strongly suggests that the state management and tool use capabilities fostered by Research and Web Frontier really shine in these very long interactive tasks where other systems might get lost or bogged down.
Okay, what about the goal-oriented tasks? GAIA often involves complex planning and using multiple tools.
Right. On GAIA, WebResearcher achieved 72.8%. This again surpassed strong proprietary models like Claude 4 Sonnet at 68.3% and OpenAI o3 at 70.5%.
So it seems adept at orchestrating those multi-step plans and juggling different tool outputs effectively.
That's the takeaway. The architecture seems to be mitigating those key failure nodes related to context management in complex planning.
And on frames, that's more of a RAG benchmark, right? Synthesizing from provided documents.
Correct. There it hit 84.8%, which was slightly ahead of competitors like DeepSeek v3.1, 83.7%, and OpenAI o3, 84.0%. Solid performance confirming its synthesis capabilities even in a more constrained retrieval setting.
The consistency across these diverse benchmarks is pretty compelling. But we really need to talk about the ablation study. This is where they tried to prove it wasn't just the fancy Web Frontier data doing the work, but the ITER research structure itself.
Yes, this is the crucial architectural validation. They needed to isolate the effect of the iterative inference paradigm, so they set up a comparison. On one side, the full WebResearcher system using iterative training data and iterative inference. On the other side, a baseline they called mono-agent plus iter.
Okay, what's that?
The mono-agent plus iter was trained on the exact same high-quality iterative data from Web Frontier. So same training data. But, and this is the key at test time, it was forced to use the old-style linear mono-contextual inference, just accumulate everything.
Ah, okay, so same knowledge, different reasoning structure at inference. What happened?
The results were pretty clear-cut. On HLE, the full WebResearcher scored 28.8%. The mono-agent plus ITER, only 25.4%.
So a 3.4 percentage point difference purely down to the inference structure.
Exactly. That delta is the win for the architecture itself. It strongly suggests that the periodic synthesis, the forced filtering via the report, the focused workspace, that iterative mechanism is fundamentally what drives the improved performance on these long, complex tasks. It's not just the better data, the architecture lets the agent actually use that data effectively over time.
The data makes it smart, the architecture keeps it smart during the task.
Well put. And this architectural advantage shows up in the agent's adaptive tool use behavior, too. They analyze how the agent used its tools depending on the benchmark.
And it changed its strategy.
Dramatically. On HLE, the academic benchmark, the agent was concise. It heavily favored the TextScholar tool that made up over 25% of its tool calls. And the reasoning chains were short, averaging just under 5 turns. Get the specific info, synthesize, answer.
Makes sense for that kind of task. But BrowseComm, the web navigation one.
Completely different story. Here, the dominant tools were basic search, over 56% of calls, and the visit web page tool, almost 40%. And the average reasoning chain length, it exploded to over 61 turns per task.
61 turns on average.
Wow. Yeah, and they mentioned some problems required over 200 interaction turns.
And the agent managed that without falling apart?
Apparently so. That, to me, is the real empirical evidence for the iterative paradigm. Being able to maintain focus, orchestrate tools, handle messy web data, and synthesize findings across hundreds of steps without succumbing to that context suffocation or noise buildup. That's what the architecture enables.
Okay, one last piece of validation. The test time scaling analysis. Did their research synthesis framework actually boost performance as they added more parallel agents?
It did. They showed results for HLE, for instance. The baseline with just one agent got that 28.8% score we mentioned. As they increased $1, the performance consistently climbed. When they used $116 parallel researchers feeding into the synthesizer, the score reached 36.7%.
So a clear positive correlation. More parallel exploration and synthesis leads to better results.
Yes. Though they did note, as you'd expect, diminishing returns. The biggest gains came early on, and performance started to plateau a bit for a 1 values greater than 8.
So a practical trade-off. 1 in $8 might be the sweet spot for performance versus compute cost.
Exactly. It suggests that configuration probably captures most of the benefit from diverse exploration without excessive redundancy or overhead. #outro.
Okay, so let's try and synthesize all this. Looking at the whole picture from the Tanguy Lab's work here, it really feels like a marker, doesn't it? A signal that we're moving past one era of agent design.
I think so. The implication seems pretty clear. It's a pivot away from just trying to linearly cram more into context.
Right, leaving the age of linear accumulation.
And entering an era focused on Markovian synthesis, iterative state management.
The two core pieces seem so complementary. You have research, the architectural innovation, directly tackling that fundamental context bottleneck for long tasks. It forces synthesis, filtering, condensation.
Instead of just accumulation. And then you have Web Frontier, the sophisticated data engine, making sure you actually train the complex tool use and reasoning skills needed to make that architecture work effectively. It's really a full-stack approach to scaling cognitive ability.
And it shifts the focus, doesn't it? Maybe the core challenge isn't just raw memory capacity anymore, bigger and bigger context windows, 256K, a million tokens, whatever comes next.
Perhaps not the only challenge or even the primary one for these kinds of tasks.
Because when you look at benchmarks like BrowseComp, demanding hundreds of coherent interaction turns, maybe the critical frontier is improving the memory fidelity.
Exactly. How good, how dense, how noise-resistant can we make that research report? Can we learn to compress truly complex, multi-source, multi-turn discoveries into a constant-size state representation that robustly captures the necessary information without degradation?
That focus on iterative state refinement, on the quality and density of the compressed memory, rather than just the sheer size of the raw history. That feels like where the truly unbounded reasoning capability might unlock.
It really could define the next stage for building these powerful, long-horizon agents, a fascinating direction.